Introduce our sixth speaker, Associate Professor Engineer Dr. Yau Yat Huang. He is a well-known international M&E engineering expert and has been practicing as an M&E engineer for the past 18 years. He has also published numerous numbers of technical papers in very reputable thermal science and mechanics journal worldwide. He is currently the M&E Principal Consulting Engineer at UPUM Private Limited, University of Malaya. Without further ado, please welcome Associate Professor Engineer Dr. Yau.
Okay, thank you, Chairperson, MC. Today I'm going to talk about this guide to green building design in Malaysia. Actually, we have a large group of people here, and I'm representing the whole research group. Okay, this project is between UPUM, which is University of Malaya, and CREE, Construction Research Institute of Malaysia. Okay, so we have come up with a draft on the green building design in Malaysia. We have chosen few case study that we believe that can help the design of green buildings. So if you look at that, we have 6 chapters here. Chapter 1 is talking about the control system. Chapter 2 is talking about the energy savings using heat recovery devices. Chapter 3 is about the climate change impact, and we have heard about climate change openly. Okay. What is climate change here to the ACME system in buildings, especially in green buildings? Because green building and conventional building, there are differences. They have differences between the two. Okay. Number 4, we have also this energy analysis of green office building in the tropical climates. And number 5, we have done some ventilation study in green buildings. Number 6, this is a very hot topic because as you know that now the split type A AC system is a norm and affordable to everyone. So we are affordable, and therefore the impact of climate change is there. So some data must be sorted here. Must be. Okay. So chapter 1. So we have the control engineering study to improve energy efficiency and thermal comfort in green buildings in Malaysia. Basically, we have the thermal comfort parameters inside there. Okay, the S-ray standard 552010 is used as a guide for us. But as you know, that S-ray is actually used in the temperate country, and it is developed in the temperate country as well. But we have no choice; we use it here because we don't have our own standard on this, which is the thermal environmental conditions we adopt. Okay, so in this case, we do something on that, and we try to localize it here in Malaysia. Okay, so what will affect thermal comfort? I think these are the parameters here. Number 1 is the human activity level. Number 2 is cladding insulation. So you see, our cladding insulation is pretty much different as well from the temperate countries. All right, they have a very thick claddings, especially during winters. And they get used to dry climates. For us, we have a very sticky condition. Do you agree?
Yes.
So if you go outside there, you come back here, you feel very sticky. And if you don't get used to it, you have eczema as well. Right? The red spots. You don't get used to the humid condition, you have eczema. Okay? And you have to apply some mucus cream or whatever medicines. Right? So, and then we look into the mean radiant temperature, which is MRT, and the mean radiant temperature is one of the key factors to determine comfort level. Alright? Then RH. So we have very high RH here. RH, in fact, is an indicator whether you have a high humidity in the space. Okay? Air temperature, that is the sensible aspect of it. Okay? And air velocity. So the ventilation inside here, whether the ventilation, you want it to be 0.2 meter per second below or above. So if you look at the temperate country one, they want a very low ventilations. So they don't want draft. But the Malaysians, we need some draft there. Why? Do you know why? So why is it always when you design, you have to design more than 1.2 meter per second for Malaysian buildings? Because one of the reasons we get used to the sticky condition is very high moisture. Okay, if you don't have draft there, the moisture is there. So you want some draft there to feel comfortable, right? So to the extent that if the SDME system couldn't work correctly, you have to provide some personal ventilation, right? Personal ventilation means use a fan there. Okay, maybe you plug in just beside your laptop. The fan, little fan. Alright? Okay, that's one of the example. But the proper personal ventilation is it's not easy, you know. You have to really design. If you have heard stratum, you know, stratum ventilation, you go into Google, you Google stratum. Okay? So that's another way of doing that, but it's complicated. Now, this one is actually the skill. Okay, used in the standard. Basically, it was developed by Fenger, the Professor Fenger. You can see that it is from +3 to -3, and that carry the meanings as well. Okay. Now, a bit of theory here. If you look at that, this is the formulas for mean radiant temperature. It's a square root of blah 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 blah. Okay. So this you have to leave it to the researcher like me, that we look into that, and we need to collect enough data. As mentioned by previous few speakers, including Dr. Badru, you know, we are pretty much lacking of data in this country. In fact, we don't have data. If you can find any data on mean radiant temperature for Malaysia, please let me know. You know, I will not spend my time to crack my head. So that's none in this country, and therefore we have to look into that. And this will have impact to the control. Why? Because the control system will use a sensor to look back into this temperature. So what's the feedback loop here? Is basically your space temperature, and your space temperature will have some impact to this, which is G. G here is actually a groups, the black box, the black groups temperatures. It's a special, you know, special equipment which can measure the group's temperature. The group's temperature finally comes with this complicated equation, and you have a mean radiant temperature. With the mean radiant temperature, you can go into X-ray tools, thermocouple tools to calculate the mean radiant temperatures. So this one is actually recommended by MS 1525. 23 to 26 degree. In fact, many industrial players question this. And many people actually ask me, why 23 to 26 degree? Who say that? You know, the MS 1525 say that. Alright, but what are the scientific basis here? You know, have you demonstrated that this will be the most the comfort level? You look at the literatures, some actually, if you look at some of the work of Professor Chandrasekhar from Singapore, which is closest to us, he recommended 26.3 degree, right, to the tropics. But then you have to ask a question here. In Singapore, they have heat islands effects. They have densely built buildings. Here we don't have. We have a scatterly built buildings. Have you seen any densely built buildings area? You can really find, you know, you can't find like this. So the thermal buoyancy effects, they are different, and you cannot actually adopt the 26.3 degree, let's say from neighbor closest Singapore. So something like this. And if you look at that, another interesting issue here is RH, 55% to 70%. So you look at that, why 70%? Okay, X-ray set it the threshold limit 60%, no more than 60%. If you have exceeded 60%, that means the fungus growth is imminent in your building, fungus. So that's very dangerous. Imagine the fungus will go deep into your lung and mutate. So this is also something that we have to take care, because the IEQ is one of the crucial conditions in green pass, right? As mentioned by our speakers. Now, air movement. So air movement here, if you look at X-ray standard, X-ray recommended less than 0.2 meter per second. Why 0.5 here? No, for example, here is 0.5. Why 0.5 here is way, way beyond the X-ray recommended standard. So a lot of arguments here. Because the more air movement that you have, okay, the more energy you have to use. So if you cut it down, I mean, you agree, right? So in this case, again, there will be arguments. So we have to go back to the scientific research and to prove that whether people, Malaysians, whether they can accept this 0.5 meter per second, or they can accept the lower one. Okay, and the outdoor design condition. This outdoor design condition, again, it is questionable as well, because the impact of climate change. We know that the climate change is there, and how much the climate change. So that's also a question. So all this, go back to the key question, how you, because your control will depend on all these parameters. Okay, this one is our code of practice for IAQ, indoor air quality. You can actually download this from our Dutch website, Department of Professional Safety and Health. Okay, I will skip this. This is the ISO standards. Now, what is the choice that we have for control system here in hot and humid climates? So one of the choice is BAS, but this is very expensive. Okay, and you see it mainly consists of digital controller, the few devices, and workstation equipment. These are the three key components. So can you imagine the payback period for this? Have anyone studied on this? I don't think so. See, in this country, use the climate of Malaysia, use the building in Malaysia, and study this. So I don't think you have any data on this. That's why UM is trying to provide this. Okay. This one is a schematic of it. All right, and my student. In the afternoon, in the workshop, we will discuss about this in detail. Okay. So this is another schematic, which you can see that the fuzzy logic control is used. Okay, because the fuzzy logic control can be used to control the fan speeds. Used to be just use the lookup table, which is very slow, and you cannot respond immediately. So if you use fuzzy control, it is quicker. Okay, so the damper as well. All right, so you can see this is the indoor zone, the outdoor units, and coupling with the AHU. Okay. All right, this is the schematics. Okay, and this one we have done a case study in cream building. The existing cream building in Mama Raya. Okay, so this is a schematic of that. Okay, that's the chapter 1. Chapter 2, I think I have to go. It's actually lunchtime. All right, I will split it up. Okay, now energy saving study using heat recovery devices. So as mentioned by Dr. Badru as well. DNB research also, they have done some heat recovery study as well using Desiccant, right? So in this case, in UM, with joint venture with CREAM, we have chosen few possible heat recovery devices. Number one is a run-around coil heat exchangers. Okay, so if you look at that, this is the run-around coil heat exchanger. It's basically playing with the hot air and cold air. Okay, and the detail we will discuss about this in the workshop. Okay, and this one is the desiccant valve. Okay, desiccant valve, which because we are in a humid climate, we want to get rid of moisture. If you have moisture inside there, you cannot get rid of moisture. You have as simple as that. You have sick building syndrome because you have fungus, and your system, your ACMV system, basically cannot work with fungus. Okay, this one is a heat pipe heat exchangers. So this is a passive device. Heat pipe does not need any external force to make it function. Okay, so again it's playing with hot air and cold air. It's basically the heat and mass transfer happen in the two-phase flow of the pipes. And this one is a black heat exchanger system. Okay, so these are the few heat recovery devices chosen for the case study. Okay, there are some benefit here. Number one is capacity reduction for cooling. Number two is reducing energy consumption. Number three, reduction of annual cooling energy consumptions. Obviously, it will lower the operating costs. Okay, and finally, it will improve the indoor air quality in the building because these devices can get rid of the moisture. The main problem in Malaysia is moisture, which is the latent load. So you can get rid of the sensible load, but you cannot get rid of the latent load. Okay, the moisture capacity in the space. That is a challenge to all M&E designers. So you size up the coil which is not big enough, which is the coil is not, or you oversize the coil by 3. That's what happened. So it's very cold, okay, and you use a lot of energy, and then you reheat it. That's even worse. So in Singapore, you cannot reheat it. It is illegal to reheat it. In Malaysia, we are still allowed, right? So I don't know when, maybe sometime later they will just stop it and you cannot reheat it. I think you have a problem. So you oversize by 3, your owner will feel very unhappy because paying a big bills. Am I right? Okay, and then you reheat it back. You use a heating coil to reheat it back. So it's not green. It is not green. Okay, and obviously this will create a global warming because you have carbon emission, you have emissions, and the entropy will be there, and the climate change, eventually the climate change impact will be there, and there will be temperature increase, the outdoor temperature increase. Okay, so that's chapter 2. Chapter 3, we are talking about the climate change. So that's lead to the climate change here. If you don't do that now, okay, you don't cut down the energy use, you don't use the technology to cut it down, then you keep on burning, okay, you can burn, but the impact of climate change is there. And eventually, you have to size the coil bigger and bigger. Why? Because you need to cool it down, you know? The outdoor temperature is getting higher. You want to lower down the temperature, you want to get rid of the heat from inside and throw it outside. So the size of the coil must be bigger and bigger. Okay, so we make a case study. We compare between green and non-green building. Okay, and you can see that that's what happened. Climate change in Malaysia. Actually, they are increasing all the time. You can see the curve here from 1972 to 1997 and whoops. Okay, there are few places here, Kuching, Kota Kinabalu, Kuantan, EJ. So we have chosen few locations, and maybe just click it here and you can have a look on the YouTube. Oh, I'm sorry. No, it didn't work. Okay. I'll skip this. Okay, I'll skip this. Now, we have referred to some literatures here, and you can see that in developed and developing country, in terms of total energy consumption, building accountable for more than 40%, which is correct. Our view previous speaker, they have also quantified this, and approximately 30% of the overall greenhouse emissions. That's how serious it is. Okay. And building climate change impact can be seen in terms of changing patterns in cooling and heating demands. We have to investigate this. Energy consumption and peak demand, carbon emission and physical structures. Because we have to predict what will happen to our SCMP system. Let's say you put this SCMP system in the green building, it will last for another 50 years. What will happen to this SCMP system for another 50 years, for another 80 years, for another 100 years? So can you predict that? Because that building lifetime will go with your system. So this is actually a cycle. So climate change will have impact to the building, and of course building will emit greenhouse gas emissions because you burn, right? You have the mechanism there, and the emission will be there. So we have done this case study. Okay, we have investigated these three objectives here. Number one is the indoor condition. Number two is the current cooling load, and we estimate the future cooling load. So we estimate the future cooling load by the year of 2020, the year we achieve advanced country status. Okay, and then the year 2050. Okay, and the year 2080, we use a software called Transit to estimate this. I have to be very quick, okay? We'll skip. And these are the profiles. The data that we have collected. Skip this. And you can see that we even have the year 2080 profile. Okay? And this is the building built in the Transit. This is actually the building. Okay? We have done it for Cyberjaya Tenaga as well as the green buildings. Okay, I'll skip this. And you can see the cooling load is going up year by year. Okay. There are some conclusion here. All right. As you can see that the cooling load is, as the design cooling load is to 1,000 kilojoule per hour, the system might not be able to provide sufficient cooling load to the office space in the future, as the maximum cooling load needed in the year 2080 as USD 332,000 kilojoule per hour. Alright, so that's chapter 3. And chapter 4 is about, we have done some energy analysis on green office building. Okay, so but I will skip this as well. I just want to go to this stage. So we go with benchmarking, okay, energy benchmarking, and we do some, we have done some walkthrough audits. We have some general energy analysis, and we go back to the dollar and cent investment grade analysis. Okay, to cut it short, we go straight to the option. Okay, so option A is actually to retrofit. Isolation, main parameter measurements. Option B, we retrofit, isolation, miscellaneous parameter measurement, and option C, you do the entire facility. Okay, and option D, you calibrated numerical modeling. You model it. So all this detail will be discussed again in the workshop. I hope everybody will join. Okay. So these are the methodology. Okay. Number one, we have literature review. Number two, we have design and build info acquisitions. Number three, we have measurement verification, MMV plan preparation. D, data acquisition, measurement and verification. And E, energy analysis. Okay, that's chapter 4. Chapter 5, we have done some safety simulation on the green buildings. I will go straight to the result, okay? Just to cut short the presentation. Okay, this is actually ST building, Cyberjaya Tenaga. Okay, it's a diamond building model in the software called Fluence. Okay, Fluent. And you see, this is the machine. we mesh it, that means we cut it, chop it down into very little elements. And this is the data, okay, the iterations. Alright, you can see the hot spot is here. That means the thermal buoyancy, the hot air effects is going up. Okay? And here you can see the wind directions. This is a side view. Again, this has proven that the hot spot is actually at the top, the red color. Okay? And this is the top view. Alright? Basically what we have done here, we have done a thermal buoyancy study for green buildings because in our standard we assume that every floor the same temperature. It is not right. It's not true. Okay? So when you size your chill water core, all this, if you assume that every floor the same temperature, the same thermal buoyancy effect, that's wrong. So to the M&E consulting engineer, that if you assume that every floor the same, then obviously the coil will be oversized. Simple as that. Okay, so chapter 6, which is the last chapter, we are talking about speed units. Okay? Okay, I don't have time to go through this. In fact, I have some YouTubes. But let's skip this. Now, how an AC system is selected in existing market? I think Engineer Louis has said now, expert system, okay, the rule of thumbs. You don't need any, you just need your experience, and it's roughly about 168 something like this. Okay, but if you use rule of thumb, either you get it right or you get it wrong. Okay. So as a result, the power consumption rises due to inefficient AC system because it is, rule of thumbs. Now here in our research here, we have used WebCYC website, the software to simulate the climate change effect on a split AC system in commercial building from 2020 to 2080, because we believe that with the green effects, green building effects, green design, okay, your system is going to last for a long time, and you have to predict this. So on that basis, we have analyzed impact towards AC system due to outdoor ambient variation in futures. And number 2, we have studied the impact of suction line heat exchanger. We apply heat exchanger in the existing AC system and subjected to weather variation in future. So we have to predict, because you can see that the split system is now affordable to everybody, and everybody needs it. It's a need rather than an options. Okay, so the impact to us is serious. Okay, how the split unit works, I think I will skip this. I will go straight to the conclusion again. Okay, this one, climate change. This is how we do it. Okay, number 1, we generate the world weather file generator for KL. Because to predict it precisely, we need to use the local weather data file rather than the OC ones. Okay, we generate our own one, and we developed together with University of Southampton, in fact. Okay, using the model from Intergovernmental Panel on Climate Change (IPCC). Okay, and the climate data for KL is used in the software to get precise results. Okay, so we have done this for green building, which is a low-cost building at Raya. So this is the data that we have collected, and this will be included in the guidelines for everybody use. Okay, so this afternoon, again, you're welcome to give us feedback on research study that we have done. Okay, I will skip this. All right, and skip this. So high. Okay, these are the outputs. The high sensibility factor, characteristic of the heat exchanger, suggests that it should be used in machine room applications. Again, a standard is needed to review the efficiency requirement of all AC systems after certain periods, such as every 10 years. Okay, in order to reduce power demand by AC system due to climate change. So, because of climate change, your AC system also got to be reviewed. And if you know that every decade you have 0.6 degree of increase, so it is serious to your power consumptions. All right. That's all from me. Thank you.